Hi all, welcome back to this series of lecture on dynamics and controls of linear systems. I'm Aman, and this is the lecture 2 in the series. So before starting, let's recall what we did in the last lecture. So in the last lecture, we did some overview of the linear systems. We looked at its solution and also when is the linear system stable. Then we went on to have a look at how can we control a linear system. We looked at what is an output and what if we have a full state feedback and how can we control a linear system and how can we stabilize an unstable linear system. All these things we saw as an overview. Today, in today's agenda, we'll go deeper into the linear systems and in the solution of the linear system in particular. We'll also look how the solution changes because of the transform coordinates and why transforming the coordinates of a linear system is beneficial for us. So with that, we'll start the lecture. So, so let's first write uh, what a linear system is, just to reiterate what we said in the last lecture. X dot is equal to ax, where x belongs to some Rn, a belongs to some Rn cross n. So this is a linear system. Its solution was x as a function of time, like at x at time t is given by e to the power at dot x naught, where e to the power at is equal to this Taylor expansion uh, of the matrix in the power of the exponential. But as it turns out, calculating this exponential matrix is very difficult because of you have to calculate each and every term in this series. So this is difficult to calculate. So to make this calculation easy, we apply some methods which we'll look in the today's lecture. So before looking at that method, let's look at the eigenvalues and eigenvectors of matrix A. So let's say the matrix has a this let's look at the eigenvalues and eigenvectors of matrix A. Here is the eigenvector xi and lambda is the eigenvalue. Now um, combining all these vectors and clubbing it into one single vector, let's call this vector t. So t is a R n cross n matrix in which each column is an eigenvector of a matrix A. These are the eigenvectors of matrix A. And then let's call a D matrix in which it's a diagonal matrix and uh, its diagonal elements are the eigenvalues of matrix A. Now we can write this equation, uh, this eigenvalue equation into a matrix form as follows. So take a moment of pause and just think what I have written here. Here, uh, A matrix multiplied by its eigenvector matrix is equal to eigenvector matrix multiplied by the eigenvalue matrix. If you'll see, this is this equation 2 and equation 1 are actually the same, one and the same. This I have written for multiple eigenvectors and values, and this one is for single eigenvalue and eigenvector. So, uh, moving ahead in this, we can say that A can be written as T inverse, or D can be written as T inverse A T. And this in particular is called eigenvalue decomposition, or this is called eigenvalue decomposition of A, eigen decomposition of A. Now, uh, uh, moving ahead, now we'll see how can we use these results in simplifying the solution of initial linear system. So let's call transformation of state. Okay, so let's assume we transform our existing coordinates x to tz, where t is that eigenvector matrix. Why we are doing so, you'll see in a minute why how this simplifies our solution of the x dot is equal to ax equation. So let's say x is equal to tz. So let's put it in our dynamic equation. X dot is equal to ax. Before continuing, this also means that x dot is equal to tz dot. So putting these two in this equation, we'll get t z dot equal to a t z. Also, which can be written like z dot equal to t inverse a t z. And here you can see a familiar term which we derived a little while ago. So we can now write this equation to be z dot is equal to dz. Now, the solution of this equation can be written as z equal to e to the power dt z naught, so where e to the power dt equals I plus dt plus t square by 2 factorial, etc. So, why is this equation so helpful? It turns out that e to the power dt is actually e to the power lambda 1t, e to the power lambda 2t, e to the power lambda nt in the diagonals. Let's say diagonal matrix. So this is easy to compute compared to what we saw e to the power 18. And this helps us think about the solution of the equation in a simplified manner. So this is what why we took this transformation in the initial place. This transformation. So let's now compute let's try to find a relation between e to the power 80 and e to the power dt. So So as we already know, e to the power at is equal to I plus at plus a square t square by 2 factorial plus a cube t cube by 3 factorial, etc. We can write this as I plus t d t inverse t plus t d t inverse t d t inverse t square by 2 factorial, etc. And t d t inverse t d t inverse t d t inverse t cube by 3 factorial, and so on, which actually can be written as t inverse. This I can be written as t inverse plus t d t inverse t plus t d square t inverse t square by 2 factorial plus t d cube by t inverse t cube by 3 factorial, and so on. Now we take t on one side, t I plus dt plus d square t square by 2 factorial plus d cube t cube by 3 factorial plus, and t inverse on the other side. It turns out that t e d t inverse, this is actually e to the power d. So this tells us that the relation between e to the power at and e to the power dt is t e d t inverse. Okay. Now let us look at the final solution of the equation once again. So if x dot is equal to ax, then the solution was xt equal to e to the power a t x dot, which by this relation can be written as x t equal to t e to the power dt t inverse x naught. Okay. We also know that if we transform the equation to x is equal to tz, then the solution becomes zt equal to e to the power dt z naught. Correct? Now let's see how are these two related. So if you see, t inverse x naught is actually z naught. Why? Because x naught is equal to tz naught and z naught equal to t inverse x naught. Now e to the power t z naught dt z naught is actually zt. So if we can see it from here, it's zt. So basically here we had some initial condition. We transformed it to z naught. We computed the solution to that equation zt, and then we transformed it to that back again. So this is xt, which is exactly like this. So this is how you should think about of your dynamic equation. Uh, like let's say you have uh, x dot equal to ax as a system of equation. In your mind, you should directly transfer from here to x is equal to tz, and which gives you zt equal to e to the power dt z naught, and xt equal to t e to the power dt t inverse z, x naught. So in your mind, you should, whenever you see a system like this, you should jump directly to this solution, which is because e to the power dt is simpler to calculate. So in today's lecture, till this we have done, uh, and we'll do stability analysis in the. We'll go deeper into the stability of a linear system in the next lecture. Till then, thank you.